Hi, everyone. Thanks for tuning in. I'm going to talk about a recent work on black box separation result for zero knowledge arguments. This is joint work with Kermit Hazai and Rafael Paz. A fundamental question in cryptography is to understand what are the minimal assumptions for a cryptographic task. And a powerful tool in the space of when we are trying to identify the minimal assumption is a black box separation result. This was initiated in and studied in the seminal work of Impagliato and Goldreich, where they showed that there exists no black box construction of a key agreement from one-way function. I'm going to talk about what a black box construction is. I just want to point out that since this work, there have been several results trying to identify boundaries of what's possible and what's not possible under the restriction of a black box construction. Here are a few restricted to the case of separating from one-way functions. So what's a black box construction? Well, specifically in this work, we are going to deal with a fully black box construction where we require both the construction and the security reduction to be black box. So let's take a primitive Q based on a primitive P. We say the construction is black box if the primitive Q accesses, the code for Q accesses the primitive P in a black box way. The security reduction, on the other hand, is considered black box if this reduction, which would be an adversary for the primitive P, accesses the adversary for Q and P in a black box way. Now, since we're going to talk about zero knowledge arguments, I sort of want to point out zero knowledge arguments from one-way functions. We're talking about Q as zero knowledge arguments, P is one-way function, and you want the construction to be black box, and you want the security reduction to be black box, and specifically it should be black box simulation, which means that the simulator in zero knowledge accesses the verifier in a black box way. I'm not going to define zero knowledge. This whole session is about zero knowledge, and so I'm going to go straight into what this talk is going to be about. So we are interested in understanding the round complexity of fully black box construction of zero knowledge. Now, let's ask first, what do we know for proofs? And let me just again restrict here that we're only going to talk about proof systems with negligible soundness. The very first work of Goldreich and Oren showed that two round zero knowledge proofs and arguments exist only for trivial languages, that is, for languages in BPP. This was extended by Goldreich and Krawczyk for black box construction, not fully black box, but just black box constructions, and show that for any language that has a three-round black box zero knowledge proof or argument, the language must be trivial. And more recently, Katz showed that if a language has a four-round zero knowledge proof, again with black box simulation, then the language must be in CoMA. And in particular, if an NP complete language has a four-round black box zero knowledge proof, it would mean the polynomial hierarchy collapses. What about five-round? Well, Goldreich and Krawczyk showed that there is a five-round black box construction of a zero knowledge proof for all of NP, assuming collision-resistant hash function, and some recent work that also shows how to make this a fully black box construction, although that's still folklore at this point. But let's ask, okay, so can we do better for zero knowledge proofs? Can we do using one-way functions? Well, no, there are a few lower bound results here. In joint work with Rafael, we showed that constant round zero knowledge proofs fully black box based on one-way functions can only exist for languages in this class that's called BPP with a collision finder. Oracle, again, if NP languages have zero knowledge, it's unlikely that NP complete languages, all of NP will have a constant round zero knowledge proof based on one-way functions. Another sort of closer result here was proved by Gordon et al., where they showed that if it has a constant round zero knowledge proof based on one-way permutations, then the language is in CoMA. Just a little bit of color coding here. Green means black box and blue refers to fully black box. In essence, the status for zero knowledge proofs is essentially resolved, at least round complexity wise. 4 is not possible. 5 is possible based on collision resistant hash functions, but not based on one-way functions or permutations. So again, this talk is about arguments. So let's ask, what do we know about zero-knowledge arguments? Goldreich-Orent's result and Goldreich Krawczyk's result also extend to arguments, while Katz's result only holds for proofs. So on the positive side, Bellare et al. Showed that you can construct 4-round zero-knowledge arguments for all of NP based on one-way functions with a black box simulator, but the construction is not black box. So it's not fully black box. More recently, Pass and V showed that there exists 6-round, respectively 7-round constructions that are fully black box based on one-way permutations and respectively one-way functions. This was more recently improved in a work of mine with Hazai and independently by Kurana et al., where we showed that 4-round can be based on one-way permutations and 5-round based on one-way functions. So the state of affairs here is essentially like the proof system, except for a small gap. We know that we can construct 4 rounds, but you need one-way permutations. The question that remains here is, can we do it based on one-way functions? Or do you need 5 rounds to do based on one-way functions? And this is the question we address in this work. And the main result here shows that only languages in CoMA have 4-round fully black box zero-knowledge argument based on one-way functions. So in a sense, again, here we have a primitive where you can do it based on one-way permutations, but you cannot do it based on one-way functions in a fully black box way. So now I'm going to go into the technical details of this construction. I'm going to start with some intuition. Basically, what I would like to do is go over the Goldreich Krawczyk lower bound, and then the Katz's lower bound, and then go into our construction. So I'm going to start with the seminal work of Goldreich and Krawczyk, where they showed that 3-round zero-knowledge proofs and arguments can exist only for languages in BPP. And in some sense, the template initiated in this work is what's sort of used in most lower bounds, at least when it comes to zero knowledge with a black box simulator. So here is a schema for a 3-round protocol, 3-round zero knowledge protocol. Now, since it has a black box simulation, how does the simulator work? Okay, given any malicious verifier, the simulator uses rewinding. This is essentially the technique that you have when it comes to black box simulation. And given that this has only 3 rounds, you can rewind from the 2nd round to the 1st round. So the lower bound begins by first defining a malicious verifier. And this malicious verifier is something that generates a new random message for its 2nd message in every rewinding. The idea here is to construct a verifier that sort of makes rewinding useless. Since there is only one message, so the verifier has a random tape that it uses the random tape to generate the 2nd message, but we want in every rewinding to generate a new random message, in a sense, a new random tape, and then with that generate the message. And this can be easily done for, you're defining a malicious verifier. Just imagine that this verifier will apply some PRG on the 1st message to generate the 2nd message. So the 2nd message becomes random, and in every rewinding, you will get a new 2nd message. So once you define this verifier, the lower bound proceeds by analyzing 2 cases. So case 1, consider, since our simulator is black box, let's throw this verifier on the simulator and ask, okay, case 1, for every no instance of the language, the simulator with this verifier fails, meaning does not output an accepting transcript. This is case 1, and case 2 is the complement, which says that, well, if for all x and l it does not fail, then there is some particular no instance on which the simulator outputs an accepting transcript. Now the lower bound, you can see that in case 1, if case 1 holds, then it means that the simulator on this verifier fails on every false statement. But on the other hand, you can show that the simulator on this verifier on a true statement will always output an accepting transcript. And this is because for this malicious verifier, if you look at how it interacts with the prover, the view of this verifier with the prover is identical to an honest verifier. This verifier only differs when it comes to rewinding, not in an execution. So if the execution with the prover is the same as the honest verifier, then the simulator must simulate this verifier and output an accepting transcript on true instances. So you have this dichotomy: on true instances, it will output something; on false instances, it will not output. So this simulator with this verifier can decide this language. And this verifier is in polynomial time. So the simulator with the verifier is in like BPP. So you have that this language is in BPP. So if case 1 holds, we know that the language is trivial. But what happens if it's case 2? There is a single no instance on which the simulator outputs an accepting transcript. And now we're going to show that this cannot happen by breaking soundness. So case 2 cannot occur if you give me a zero knowledge proof system. Okay, so let's go deeper into case 2. We want to show how does this lower bound work. So we have a particular no instance on which the simulator outputs. Now I'm going to construct a malicious prover that's going to break soundness. And this malicious prover in her head is going to run the simulator with the defined malicious verifier, and is going to try to convince an external honest verifier. Roughly speaking, the idea here is that this prover is going to try to take this accepting session from the simulator's rewinding to forward it outside to the honest verifier, so that whenever internally in this transcript output by the simulator, if it's accepting, we will have that the verifier externally will also be accepting. And here I should point out that since we assume a black box simulator, it means that you can assume without loss of generality that the simulator will output one of these rewinding sessions as its final output. If at all it outputs anything, it will be one of these rewinding sessions. So the goal of the prover, this malicious prover, is to pick one of these sessions and forward it outside. So to use the messages with the outside verifier internally on that session. Now, there are two basic issues when this, when you want to do this kind of a forwarding attack. First is that, the prover does not know which of these sessions the simulator is going to output. But this is okay, because there can be only polynomially many. So, let's pick one at random and forward it outside. And, if the simulator outputs with non-negligible probability, the prover will still convince with, 1 over poly of that, which will also be non-negligible. But the second problem is that if the prover, say forwards the first message outside and then gets the second message from the verifier outside and forwards it internally. Now in the rewindings internally, we need to simulate the malicious verifier's message in other sessions. Okay, in this case, it's actually easy because there is only a single message from the verifier. In every rewinding, I can just, do what the malicious verifier does, which is, apply the PRG, except in the one forwarding session that I send outside. Okay, so rewinding is okay. But now there is one more thing that we need to deal with. Now, if we are forwarding an external session internally in one of these rewindings, are we changing the distribution of the messages from the verifier in the simulator? And since we use the PRG to generate a random tape, and externally this verifier has a fresh random tape, it would not change the distribution, or at least it will be computationally indistinguishable to the simulator. So this attack essentially works by having the prover forwarding one of these sessions outside, and then hoping that this rewinding is the one that the simulator outputs as the accepting transcript. And this is essentially the Goldreich Krawczyk lower bound. So now let's try, let's ask what happens to 4-round zero knowledge proofs, right? So if you look at a 4-round, the schema is going to be something like this, where the verifier sends the first message. And once again, what you're going to have here is that the simulator is going to rewind from, the third to the second message here. The first message, again, the verifier is always going to send the same first message in all sessions, but it is the simulator can only usefully rewind from the third to the second message. Okay, and now we're going to define exactly the same malicious verifier and try to carry out the same Goldreich Krawczyk lower bound. So the first issue that we come across here is that when we have to do this, like let's say that we take the first message from outside forwarded inside, and pick one of these sessions to forward outside. The problem is that when we rewind internally, we need to simulate the third message from the malicious verifier. And now it's not as easy as just saying, okay, let me just do PRG of the transcript and send the third message, because the third message needs to be consistent with the first message. And the first message was forwarded from outside, which could have involved private coins from that verifier, and we don't have it. So how can I generate a third message that's consistent with something that is outside? At least it's not clear that we can do this efficiently in polynomial time. So the idea is, let's use some heavy hitter. Let's use a p-space oracle to invert the verifier to get random coins consistent to generate a random message, a uniformly random continuation of this first message. Okay, so I'm going to do case 2 first. And the reason is it okay for this malicious verifier to use a p-space oracle? And in case 2, I need to construct a prover that breaks soundness, but this is a proof system, which means that my prover is unbounded. So in order to simulate such a malicious verifier, this prover can make use of a p-space oracle. So case 2 actually does not get affected, even if the internal malicious verifier, if we make use of a p-space oracle. But case 1, on the other hand, is now going to break. We need this internal verifier to be efficient to say that the simulator with the malicious verifier decides the language. So at least case 1 is broken. And now, it's rightfully so. It should be broken because we cannot conclude that the language will be in BPP. We know of non-trivial languages that have 4-round zero-knowledge proofs, specifically those in statistical zero-knowledge. So this is where we're going to come with the Katz's lower bound, where he shows that if it has a 4-round proof, the language in fact is in CoMe. And here is the idea. The idea is that Merlin is going to pick a randomness, R1 through Rn, again uniformly at random, condition on the fact that the honest verifier generates the same first message with all this randomness and gives this to Arthur. Okay, and why is this randomness useful? Well, this randomness can be used to simulate a malicious verifier as defined in the Goldreich Krawczyk lower bound. This verifier uses fresh randomness for every rewinding. Now you have this randomness that has a consistent first message. So this is why this randomness is going to be useful. Let's see what Arthur is going to do with this. Well, Arthur is going to take the simulator and run the verifier, where in every rewinding it picks a random Ri, okay, to simulate the third message. And finally, well, if the simulator outputs something, then you reject. And if it fails, you accept, because you want the language to be in CoMe. Okay, so now this is going to help address case 1, right? So since you want L to be in CoMe, when you consider a no instance for L, it's a yes instance for the proof system, for the MA proof system. And the simulator on the verifier on this instance will fail, which means that we will accept. And we need to also show soundness, which means that for a yes instance, we need to show that no matter what Merlin sends, the simulator will always succeed, will always output an accepting transcript, and therefore Arthur will reject. Now, this works, except that we need to assume perfect completeness. And the reason is that otherwise there could be bad randomness that make the simulator on this verifier fail. And Merlin, as we are talking about soundness, could choose these bad randomness and thereby make the simulator fail, in which case Arthur might accept a no instance for the proof system. Okay, so if it's perfectly complete, there is no bad randomness. Okay, so this works only for perfect completeness, but Katz extends this also for imperfect completeness, and it's actually a really beautiful trick. And the idea is to test the randomness before using it. Okay, so how does this work? There's just 2 steps before you run the simulator on the malicious verifier. So you just pick a random tape, take the honest verifier with this random tape, run the simulator and see if it accepts or not. Okay, and recall, like, this is a zero knowledge system, which means for true instances, for sure the simulator will output something. For false instances, we don't know. It could be one or the other. So first you do this, and if the simulator fails, you right away accept. If not, you proceed. And now you're going to pick a random one of these R1 through Rn and fix that as the random tape and run the simulator with the honest verifier on that random tape and check if it fails. And now if it fails, you're going to reject. Okay, and you will see that these 2 simple ideas is going to fix this for even when the proof system is not complete. So I'm going to go through the completeness and soundness of this proof system. So first, let's talk about completeness. So completeness means I'm talking about a no instance for L, which is a true instance for the proof system. So if I have a no instance for L, now let's say that, look, there are 2 cases on the first step, right? Either on a random R, it fails, or it accepts. Now, if it fails, I've already accepted, and this is good, we are in completeness. But if it does not fail, it means that the simulator does output an accepting transcript. Now, so this means that, it goes to step 2, and we need to make sure it does not reject in step 2. But since for a random R, the simulator fails, and Merlin is honest, the distribution in the second step is exactly the same, which means it should also fail in the second step if it failed in the first step. So if it accepted in the first step, then it must also accept in the second step, which means I will not reject in the second step. Okay, so on a random R, the simulator does output an accepting transcript. Okay, so which means that now in the third step, we need to make sure that the simulator on this verifier with this randomness will not output an accepting transcript. It did output for a single randomness R, but we need to make sure that when we construct this malicious verifier, that it will no longer output an accepting transcript. Okay, because only then will I accept. But this is exactly case 2 from the previous slide. We know that for this malicious verifier that uses a fresh random tape on a no instance of the language, the simulator will not output an accepting transcript. So this cannot happen. So this is completeness. But soundness, on the other hand, is actually just a simple 4-step idea over here. You want to show that, so let's start with this, right? So on the first step, we know that since we are talking about a yes instance for L, the simulator will output an accepting transcript. So on step 1, it will not accept because the simulator has to output an accepting transcript. Now let's go to the second step. Now in the second step, well, if Merlin gives bad randomness that make the simulator output fail for a random I, then I'm going to reject it already. So let's start with the premise that for a random I, the simulator with the honest verifier with random tape Ri accepts. Okay, if this is the case, then by using zero knowledge, we know that the prover with the verifier on this random tape will also accept. Now, let's replace this verifier with the malicious verifier that chooses one of these random tapes at random. Okay, now you can see that, in the previous step, I picked the random tape ahead of time at random and fixed the honest verifier. But in the second step, it is a malicious verifier that picks one of these at random in the execution. But from an honest prover transcript point of view, these 2 distributions have to be identical. So then again, if it accepts in the previous one, this prover with this malicious verifier must accept. And now, once again, applying zero knowledge, if this accepts, then the simulator with the malicious verifier on this random tape should also accept. So just by using zero knowledge, we can conclude that the simulator on this verifier must accept, which means that in step 4, the simulator will not fail, in which case it means that we will reject. Okay, so this is essentially the idea of Katz's lower bound. Now let's move to zero knowledge arguments. So what happens when we consider 4-round zero knowledge arguments? Well, both the prover and the verifier have access to an oracle O. We're going to model this, this oracle O, you can think of it as a random oracle. Okay, so now let's walk through the same kind of idea like what for constructing a lower bound for zero knowledge arguments from one-way functions. So what happens here? Well, let's ask the question again. Can we simulate these messages? And the point is we cannot use a p-space oracle. Well, at least, unless the p-space oracle can invert the random oracle itself, we cannot use the p-space oracle. And, this lower bound can be carried through if we can use the p-space as long as it makes only polynomial queries to the oracle O outside. And so this is not going to work because we have to invert the verifier if we want to send a consistent third message from this malicious verifier. So the idea that we are going to say over here is that how about we fake these queries internally in the rewinding, right? I mean, we have to forward one session from outside to inside. In the remaining rewinding sessions, let's just make oracle queries. It might not be consistent with the oracle O outside, but let's fake these queries internally. It seems okay, except that there is one issue. Now, in these rewindings, the simulator is in fact learning something, right? Now, if we forward Q like the outside, and let's say Q, Q1, Q2, Q3 denote the oracle queries made in these sessions. Now, let's say Q equals Q2. Now, the problem is that the simulator could learn some of these oracle queries in the other sessions and use that oracle query in the second session. Now, why is that a problem? Well, if I take in the second session, if I take the fourth message that I forward outside, it could make this verifier outside query at a point that was faked internally. In which case now we can no longer conclude that if it was accepting inside, it will be accepting outside. Okay, so we can fake queries inside and go through, but the problem is that it no longer can we conclude that the outside verifier is going to accept. Now, I should point out that by faking queries inside, I should say, first of all, will the simulator work? And here is the point where we essentially use that the oracle is a one-way function. If we have to fake queries internally that's consistent with the first message, we're actually going to induce collisions in the oracle, because when I generate Q2, I don't know how the first message was generated. So I create new randomness and new queries that is consistent with the first message, and this can induce collision. So the simulator must work with a one-way function oracle, which has, it's different from permutation because there are, collisions. Okay, so this is exactly the point where we use, but still there is this problem of forwarding. And our approach here is just to say, okay, let's call this event a bad event. Okay, the event is bad if, when I forward this outside, it makes the outside verifier query make a bad query. Okay, and now I'm going to tell you how the MA proof system for the complement of L is going to work. Merlin is just going to imagine a random oracle, and it's going to create randomness and queries that are consistent again with that give the same first message, and it's going to send it to Merlin. Now, what Merlin is going to do, pick a random R and an oracle, just like the cat's lower bound, and check if the simulator fails. If not, I pick a random Ri and Qi, and I check if it fails. But in addition, I also check if this bad event occurs. If either of these happen, then I reject. Then I'm going to run the simulator with the verifier with all this randomness and these queries. And I'm going to do exactly as before, except if it fails or if the bad event occurs and rejects otherwise. Okay, I'm not going to go into the completeness. I'm just going to go into the soundness, how this works. Okay, so in soundness, recall again, we're going to do with the, we're not going to assume any perfect completeness. We're going to show how it works. So now in the first step, it cannot fail because, it must. We are talking about a true instance for L, which means that the first step, the Arthur will not accept the statement. Now I need to make sure that in the second step, let's see what happens. Well, if you give me QI and RI where the simulator fails, I reject right away, or if this event B occurs. So if it has passed the second step, meaning if it hasn't rejected already in the second step, we have that, for a random I, S accepts and B does not occur. Now, again, we're going to follow the same logic, which means that by zero knowledge, we will have that the prover on this verifier will accept, and this event B will not, bad event will not occur. And we just follow exactly the same thing, and you will have that, S with this verifier will accept without this bad event occurring, and you will reject at the end of it. Okay. Now for the true instance, of the proof system, which is the false instance of the proof system, we need to make sure it doesn't reject in the second step. That's all we need to make sure. And for this, we need to make sure that the bad event does not occur. And the basic idea that we're going to use over here is to learn heavy queries. So when we fake the queries inside, we will learn enough number of heavy queries for the first message before we simulate for the second message. Again, I am trivializing a lot over here, but this is essentially the idea. And I encourage all of you to go and read the paper. Thank you.